Hello again, everyone. We are going to pick up with the remainder of page 67. Then we'll do pages 68 and 69. So this might be a slightly longer video. So go ahead and get settled in. We're going to learn possibly the most important test in a Calculus 2 class for determining absolute convergence. So maybe write that down. And it's actually a very simple test to apply. Here's all you do. You find it. Let's say you have an infinite series here. All you do is concern yourself with the summand. So in this case, just the an, the things that you're adding up. That's what I mean. And now you replace the index by n plus 1 instead of n everywhere you see it. Divide all that by just use n for the index and take the absolute value. Upon doing the limit of that ratio, this is why it's called the ratio test, right? Because you're doing the limit of essentially this ratio here. If that value comes out to be less than 1, then you conclude that the series is automatically absolutely convergent. So super, super helpful. If that limit comes out to be bigger than 1 or infinite, then you conclude that the series is divergent automatically. Now, if it equals 1, then the ratio test is inconclusive. So it is limited. It's not a silver bullet, so to speak, but it is very helpful and very useful. But if the ratio test comes back inconclusive, meaning that you get 1 for this limit here, then you have to use another test to decide convergence or divergence. So that means you have to go back to test for divergence, or one of the comparison tests, the integral test, or alternating series test, something like that, okay? So here's an example, these two here on the bottom of page 67, that show you that the ratio test giving 1 tells you absolutely nothing about the series. So here, this series here is convergent. It's a p-series with p equal to 2, and so it converges, right? Furthermore, we know that it actually converges absolutely because, I mean, look, if you put the absolute value bars there, 1 over n squared is already positive, right? And we know that this one converges, and so the series with the absolute values on the 1 over n squared also converges, okay? However, let me show you what happens when you apply ratio test. So we take limit n goes to infinity, 1 over, and now I plug in n plus 1 into the summand, so I get n plus 1 quantity squared, divided by 1 over, and then just plug in n, and I get n squared, right? Flip and multiply, so I get, oh, and I need to do absolute value, excuse me. Now you'll notice everything is already positive, so I don't need absolute values here. I get n squared over n plus 1 squared. And use whatever method you want to verify this. You could expand out the bottom and do some L'Hopital rule. But what you notice is that they're both degree 2 polynomials on the top and bottom. So the limit is just the ratio of the leading coefficients, which is 1. Okay, now since the ratio test gives you 1, that tells you absolutely nothing about whether or not this series converges or diverges, right? And so you see we had to use another method to determine that, right? We had to use the fact that it's essentially a p-series to conclude convergence. Now coming down here, apply the ratio test to this one. What is this called, by the way? This is called the harmonic series. And what do we think? It's divergent, I think, right? However, we take the ratio test, put the absolute values, plug in n plus 1 into the summand, so you get 1 over n plus 1, plug in n to the summand, divide those two in that order, and you get limit n goes to infinity, n over n plus 1 when you simplify. Notice I don't need absolute values, everything's already positive, and this limit is also 1. So you see it's possible to have a divergent and also an absolutely convergent series where the ratio test equals 1. So this is telling us that the ratio test is inconclusive when it spits out 1. So the hope is that the ratio test does not spit out 1 very often, otherwise you have to use other tests. And so let's just turn the page to page 68 and look at somewhere that the ratio test does give us something useful. Okay, here. So this right here is the summand. This is what you would call an, right? This negative 1 to the n cubed over 3n. 3 to the n, excuse me. You could try alternating series test if you like, but maybe you don't know how n to the third over 3 to the n behaves. Maybe you don't know if that's decreasing or not. So let's just try it. Let's try ratio test and see if we can conclude that this is absolutely convergent. So we're going to take the limit, n goes to infinity, absolute value. And now remember, we plug in n plus 1, and then big division bar, plug in just n. So it's essentially like when you're plugging in just n, it's exactly the summand that you're looking at here, right? Okay, now you can see that this is kind of taking up a lot of vertical space, and ultimately what we end up doing anyway is flipping and multiplying. So moving forward, I'm just going to do that like already. So I'll jump to essentially the step that I'm writing down now because it's easier and saves a little bit of vertical space, excuse me. All right, so the key observation here is that alternating parts get killed by the absolute value. Let's remember that all the way back from section 8.1. And so that kills this part and this part here, the minus 1 to the n plus 1 and the minus 1 to the n. And then the next thing I'm going to do is I'm going to arrange it so that things that kind of look like each other are stacked on top of each other. So what I mean by that is look at the following. This n plus 1 to the third, well, it's kind of like this n cubed here, right? And now this 3 to the n looks a lot like this 3 to the n plus 1. And now this limit, be very, very careful here. We actually need to split up this 3 to the n plus 1. So this is the limit, n goes to infinity, n plus 1 cubed over n cubed times 3 to the n over 3 to the n times 3. You'll notice now this 3 to the n cancels on top and bottom. And the limit as n goes to infinity of n plus 1 to the third over n to the third, that limit is 1. Again, expand it all out if you like. You get a degree 3 on top, degree 3 on bottom. Take the ratio of the leading coefficients, which is 1. So you get 1 times, when this cancels, that's a 1 up here, so 1/3. And now since this number is less than 1, we conclude by ratio test that the sum n equals 1 to infinity of minus 1 to the n times n cubed over 3 to the n is absolutely convergent. So we'll do this one next, but we need a little a timeout here, and we need a lesson, a quick crash course on factorials. So here's some definitions for you. First of all, 0 factorial is defined to be 1. 1 factorial is also 1. 2 factorial, maybe you've heard of factorials before, but what you do is you start with this number that you see and then multiply by the next lowest integer until you get to 1. So it's 2 times 1, right? And that's just 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on and so forth, right? Now here's the key observation. 4 factorial is 4 times this expression here. But look just up above. What is 3 times 2 times 1? That's 3 factorial, right? So 4 factorial is actually 4 times 3 factorial. Similarly, 3 factorial is 3 times, well, look, 2 factorial, right? And this factorial, kind of think of it like a power. It's only acting on the thing that it's right next to. So this factorial is not acting on the 3 as well. This one is, but not this one here. It's only acting on the 2, right? So 3 factorial is 3 times 2 times 1. Well, that 2 times 1 is known as 2 factorial. And so a general rule of thumb is that n plus 1 factorial is the same as n plus 1 times n factorial, right? You can just essentially peel off the first leading factor, right? You're peeling off this n plus 1, and everything thereafter is n factorial, okay? So let's come over here now. Let's apply the ratio test. So we have limit n goes to infinity, absolute value, plug in n plus 1, and then flip and multiply, plug in just n. Everything is already positive, so I don't need the absolute value bars. I get the limit, n goes to infinity. And now let's rearrange here. This n plus 1 to the n plus 1 kind of looks like this n to the n. And this n factorial and the n plus 1 factorial are kind of related, right? Okay, so here's what you're going to do. Every time you see a factorial, there's probably going to be a cancellation with a lower type of factorial. So peel off as many factors from the front as you need. And anytime you see something raised to a power with n and some other stuff, always split that up. So this is the limit n goes to infinity, n plus 1 to the n times n plus 1, right? And this here is n factorial over n plus 1 times n factorial. Look over here, right? That's essentially what we just showed. Now the n factorials cancel. Notice this factor of n plus 1 cancels with this leftover factor of n plus 1. And so this is the limit n goes to infinity. Now it's tempting to call this limit 1. It's not though. And the reason that this limit is not 1 is because if you compare it with something up above here, like, oh, I don't know, here, you'll notice this power was fixed, whereas here, the power moves, right? The power also moves with n. And so the right thing to do is to combine this into a single expression. Since they're both raised to the n power, it's n plus 1 over n all to the n power, which can be rewritten as 1 plus 1 over n all to the n. And now this is a very, very famous limit. You could use Calc 1 methods to find this limit by, you'll notice that it's 1 to the infinity. And so you would take the natural log and then arrange it for a L'Hopital's rule, something like that. But I'll just go ahead and tell you very quickly that this is actually a limit expression for the number e. The number e is 2.7 whatever, which is bigger than 1, and therefore, by the ratio test, the sum n equals 1 to infinity, n to the n over n factorial diverges. Okay. Now, why don't you go ahead and try this one on your own? Pause the video if you like, but let's work it out. Okay, so this is what you get when you plug in n plus 1, right? You get 10 to the n plus 1, n plus 1 plus 1, 4 to the 2 times, and now parentheses, right? N plus 1 plus 1, and now flip and multiply just what you see here without the summation, just the sum and, right? So we're essentially using exactly what we see. Okay, everything's already positive. So what we're going to do is get rid of the absolute value bars, and combine and stack similar things. So here 10 to the n plus 1 is similar to 10 to the n. N plus 1, and now here we actually have an n plus 2, right? Notice this is n plus 2 right here. And then finally 4 to the 2n plus 1. And now this one here is 4 to the 2n plus 2 plus 1 is 4 to the 2n plus 3, right? Okay? And now do what I told you above. Anytime you see an exponent with like plus or minus in there, expand it using laws of exponents. There's not much we can do with this, but that's okay. And then here, 4 to the 2n times 4, 4 to the 2n times 4 cubed, right? Things should cancel. And I'm left with limit n goes to infinity, 10 times n plus 1 over n plus 2 times 1 factor of 4 cancels, right? So that'll be 1 over 4 squared. Okay, so I get 10 over 16 times n plus 1 over n plus 2. As n goes to infinity, this fraction right here in the middle goes to 1. Justify it to yourself however you like. And so the final answer is 10 over 4 squared, so 10 over 16, which reduces to 5 over 8. That number is less than 1. So by ratio test, the sum n equals 1 to infinity, 10 to the n over n plus 1, 4 to the 2n plus 1, is absolutely convergent. All right, now the next and final root test that we're going to talk about is the root test. This one, in a calculus class, it actually doesn't come up that much, but I think most mathematicians would agree that it's usually the test with the broader scope, meaning that the root test, if the ratio test ever gives you like whatever the result the ratio test gives you, positive or negative, the root test will also do that, and sometimes it works when the ratio test is inconclusive. But anyway, we're usually only going to see it when you have a whole expression raised to a power involving n. And the result is exactly the same. It's just the setup, you use the nth root instead of doing like a ratio. Okay? We're going to take the limit n goes to infinity, nth root of absolute value of this whole expression. And now rules of exponents tell us that this is the limit n goes to infinity, nth root. And now absolute values can move inside powers here. So this is 2n plus 3 over 3n plus 2 all to the n, right? And now the nth root and this nth power cancel. And that's why we usually always see it applied in this context, when you have a whole expression raised to the n power. And the absolute value of 2n plus 3 over 3n plus 2 is just itself. Everything's already positive. And that limit is 2/3, which is less than 1. So by root test, the sum 2n plus 3 over 3n plus 2, all raised to the n power, from the sum from 1 equals n to infinity of that, converges absolutely. And then finally here, why don't you go ahead and try. Apply the root test, so we get limit n goes to infinity, nth root of absolute value of this whole expression, so minus 2n over n plus 1 to the 5n. Like I said, absolute values can switch places with powers, and we can use laws of exponents to do the following. This is the nth root of minus 2n over n plus 1 to the 5th to the n. And here we see, again, the powers canceling. So this is just the limit n goes to infinity of minus 2n over n plus 1 all to the 5th inside absolute value, right? We need the absolute value. Now we can move the absolute value inside this power, inside the power 5. And now the absolute value of minus 2n over n plus 1 is positive 2n over n plus 1. So this is the limit n goes to infinity of 2n over n plus 1 all to the 5th. And if you like, you'll notice that since this power is fixed, we can actually take this limit and move it in. We've seen that. In fact, we just did that in the video where we talked about sine of pi over n, right? And so this is 2 to the 5th, which is 32, which is definitely bigger than 1. So by root test, this series diverges. And so just some concluding thoughts here. If your ratio or root tests come out to be inconclusive, then you have to do something like we did way back here on page 67, right? Where you have to apply another test to it. But if they come out to be either strictly less than 1 or strictly bigger than 1 for the root test or ratio test, then you're golden. Like that, you automatically know the result. You just have to remember the result, either divergent or absolutely convergent. However, when the ratio and root test come out to be 1, you have to do something else. You can't just say the test is inconclusive. Like we need an answer. We need to know if the series converges or diverges. One of this all-powerful root and ratio test being inconclusive is not a sufficient answer, right? It's only a stepping stone to making you do something else to find out. Okay, that's it for convergence tests. Starting in section 8.5, we learn about power series.